Okay, so 46. Let G be a group of complex number 1I minus I under a multiplication, whose following statements are true about the homomorphism of G into itself. So remind that G to G homomorphism means that f of x, y need to be f of x multiple f of y. And that's it. So we need to identify which one is the homomorphism. So basically, since multiplication already have this property in A, because your z okay, so x, how do I write it? X y bar is x bar y bar. So basically, this property is already satisfied. So all we need to check is this map indeed send element of G into G. And this is easy because when 1 map to 1, I map to negative I, minus 1, and minus I go to I. So indeed every element in G is sent to element in G. So the first one is correct. Okay. Second one, z to z squared. Okay, so basically this property still hold because xy squared is basically x squared y squared. So all we need to check is indeed the element in G is indeed mapped to the element in G. So 1 square is 1, and I square is minus 1, and the minus 1 square is 1, and the minus I square is minus 1. So basically still the same as the first one. So the first one and second one are all correct. How about the second one? How about the third one? The third one say that each k, the homomorphism has zk. Okay. So basically the xyk is still the xkyk. So it's indeed has homomorphism property. So all we need to check is 1 map to 1, right? I map to ik. Minus 1 go to minus 1k. And minus I go to minus ik. And indeed that for each k, for given any integer k, I to the power k can only have 4 choices. Basically it's the same as minus 1i minus 1 over minus I, and the same as the minus I to the k's power. So basically all these 4 choices, for any k, these 4 numbers definitely fall into, will be the element of G. So this tells you that the third one is also correct. So the answer is the first one, second one, and second one. The answer, first one, second one, and third one. So the answer is E.